The alpha collaboration at CERN has succeeded in cooling down antihydrogen atoms, the simplest form of atomic antimatter, using laser light. The technique known as laser cooling was first demonstrated 40 years ago on normal matter and is a mainstay of many research fields. Its first application to antihydrogen by alpha, described in a paper published in the journal Nature, opens the door to considerably more precise measurements of the internal structure of antihydrogen and of how it behaves under the influence of gravity. Comparing such measurements with those of the well-studied hydrogen atom could reveal differences between matter and antimatter atoms. Such differences, if present, could shed light on why the universe is made up of matter only, an imbalance known as matter-antimatter asymmetry. The researcher says that the ability to laser cool antihydrogen atoms is a game changer for spectroscopic and gravitational measurements, and it could lead to new perspectives in antimatter research, such as the creation of antimatter molecules and the development of anti-atom interferometry. About a decade ago, laser cooling of antimatter was in the realm of science fiction. Antimatter is a necessity in the most successful quantum mechanical models of particle physics. It became available in the laboratory nearly a century ago with the discovery of the positively charged positron, the antimatter counterpart of the negatively charged electron. When matter and antimatter come together, annihilation occurs, a striking effect wherein the original particles disappear. Annihilation can be observed in the laboratory and is even used in medical diagnostic techniques such as positron emission tomography (PET) scans. The alpha team makes antihydrogen atoms by taking antiprotons from CERN's antiproton decelerator and binding them with positrons originating from a sodium-22 source. It then confines the resulting antihydrogen atoms in a magnetic trap which prevents them from coming into contact with matter and annihilating. Next, the team typically performs spectroscopic studies, that is, it measures the anti-atom's response to electromagnetic radiation, laser light or microwaves. These studies have allowed the team to, for example, measure the 1s to 2s electronic transition in antihydrogen with unprecedented precision. However, the precision of such spectroscopic measurements and of planned future measurements of the behavior of antihydrogen in the Earth's gravitational field in ongoing experiments is limited by the kinetic energy or equivalently the temperature of the antiatoms. This is where laser cooling comes in. In this technique, laser photons are absorbed by the atoms, causing them to reach a higher energy state. The antiatoms then emit the photons and spontaneously decay back to their initial state. Because the interaction depends on the atom's velocity, and as the photons impart momentum, repeating this absorption-emission cycle many times leads to cooling of the atoms to a low temperature. In their new study, the alpha researchers were able to laser cool a sample of magnetically trapped antihydrogen atoms by repeatedly driving the antiatoms from the atom's lowest energy state, the 1s state, to a higher energy state, 2p, using pulsed laser light with a frequency slightly below that of the transition between the two states. After illuminating the trapped atoms for several hours, the researchers observed a more than 10-fold decrease in the atom's median kinetic energy, with many of the antiatoms attaining energies below a microelectron volt, about 0.012 degrees above absolute zero in temperature equivalent. Having successfully laser cooled the antiatoms, the researchers investigated how the laser cooling affected a spectroscopic measurement of the 1s to 2s transition and found that the cooling resulted in a narrower spectral lineup for the transition, about 4 times narrower than that observed without laser cooling.